Okay, so take a look. This is one of the data the same as the data we gave to you. I just want to visualize that, right? This is a graph. This is a PPI graph. It's clear? Okay, and since this is a PPI graph, and such that you can say, we go back to the paper again, right? So in this paper, they say, okay, when you align, you have this graph, you have another graph. Another graph go to the different species. This is the human. You could have, this is the coronavirus, and it has, infected the cat and the tiger, and you have, the similar, very similar, the graphs, similar network, and which happen in another species. And some, is not well studied. People want to compare these two network to see how similar they are. And then in this paper, this is called HUT. Go back to the paper again, right? Okay, this is already opened. For example, we want to compare this image with the image we show you here. You can say, just through your eyes, it's really hard to judge. I want to put these two pictures together, right? Just to use this graph, it's really hard to compare. Take a look. It's really hard to compare how similar this graph could be. This is the reason we need to use computational tool. In this paper, they said, okay, if some nodes, for example, right? If some nodes, I use this annotation. For example, these nodes, this nodes kind of too big, right? Okay, that's fine. So take a look at this one, and this nodes has a very specific critical position. Why? This guy compare another guy. This is kind of the guy who play in the central role, and this guy has connection with 6 another nodes, right? So the connection with this guy, connection with this guy, connection with this guy, and if this nodes, this is stat 3. For some reason, these loads got, destroyed, or these loads got damaged. In that case, this PPI network, many protein will not be function well, right? And so, take a look at this one. They may have the same kind of loads. For example, these loads. These loads play some central role, or these loads play some central role, right? You cannot just use the name to say how similar these loads could be, because this name just is the protein's name. And the protein is component, is compounds, chemical compounds. And they make something similar, although the name is different. So people compare the sequences, people compare the how loads to loads the load to load similarity, we call the object to object similarity, right? Similarity. Here it is corresponding to the load to node similarity. And the node to node similarity corresponding to sequence alignment. This is what we discussed in the dynamic programming, right? People use a sequence alignment, and such that they can give a score to see this one with this one, how similar they are, one from one network, another from another network, right? And such that you can give the score on the load-to-load similarity. This is load-to-load similarity. And such that in this paper, they mention that. They mention this point-to-point, node-to-node similarity. This is the paper talk about one type of similarity. And then another type of similarity corresponding to this, they also emphasize the topology. In this topology side, they emphasize the degree, right? They emphasize how important this loads could be. Which position it could be, how many another loads are contact with these loads, and how important these loads could be. This is to check the importance of each loads from the topology perspective. So this discussion gives you the rough idea about this paper. Now I go back to this paper again. Okay, so in this paper, and then also I make it bigger. And this part, it gives you idea what they do, and then underline it is They said, if you just take a look, the degree of the graph, this just give you the local, this give you local topology information. This paper want to calculate the global topology information. So what they do, they want to check the importance, right? So one of the task, this is go to the paper. And for the paper, I don't want to go to the line by line, right? So this part go to tell you what is the formulation. This part give you the formulation. And this part give you the formulation. And this formulation corresponding to, you have something I want to emphasize. So this is the one graph. This talk about the undirected graph. In this paper talk about. And in this graph, they also has the weight. This is the weighted undirected graph, right? This is the weighted undirected graph. And then so they use a specific symbol N to represent the adjacent loads corresponding to labels. N corresponding to labels. And they use the degree U corresponding to the degree of vortex, corresponding to how many adjacent nodes, how many labels of vortex U, right? In this case, for example, in this case, if we check the degree, so it gives the weighted undirected graph. And in this picture, you can treat each edge as the weight 1, right? And then so then if we talk about U, the N, let's say U is equal to let's say U is equal to this guy, right? The STAT. This one is the U, right? This one is the U. Let's just say this guy is the U. So if this guy, it is U, and then in that case, NU is corresponding to the labels, all the labels, right? Take a look at this one, all the labels. So in this case, all the labels corresponding to, I want to draw this guy, right? This will be the labels, this will be in the list, this will be in the list, this will be in the list, this one and this one. So in that case, I have to draw this guy, right? So since it's to write it down, take a time, I just briefly write in this way. This is the informal, the discussion of the paper. So, so 1, 2, 3, 4. Hold on. This should be 4. This is 4, right? This is 5. So it means how many nodes, how many adjacent nodes. If this is U, when we talk about the NU corresponding to all the labels. When we talk about the degree U, and when we talk about degree U, that's different. Degree U corresponding to the number of this label connection. So in this case, we have 6, right? So just be aware of these two terms in this paper to emphasize. And then so after this is the annotation, and then so and they use they compare the number of loads in each graph, and then you go to here. This is for calculate the topology and the function importance of the property. And so this is the whole section is to talk about that. And let me explain to you what does it mean for calculate the importance of, let me write it down here. Okay, so for this hub, let me write it down, HubAlign. This algorithm. This algorithm separate into different steps, right? So I will write down the steps. Let's say, can I make this one bigger? Okay, good. And then so I even want to make it even bigger. So this one, I want to change this one to be 2. Change this one 2. Okay, good. So this question, it is given right? First, I will write down the problem formulation. Given G1, V1, E1, and given G2, V1, E1, this G2, right? V2, E2, and also I think I forgot to put a weight here. So in this case, I need to erase. So in this case, we also need to put a weight here. The reason it is to count the importance, and the author also check for why this changed to be this one. Okay. Is too small or not too small? Seems very small, right? This is E2, and this is W1. Okay. Gave two graphs, and then they wanted to find a function, and which is map G1 to G2, right? And the map is G1 to G2. Actually, in the author, they emphasize it is F and V1 to V2. The best mapping. This is the main idea. Now the question it is, how do you measure this F? The author's idea it is they emphasize the important loads. They want to give more weight in the important loads. Okay, let me know if you follow me, okay? And if you have any question, you can ask. The first step, as I say, explain to you, right? So the first step, which is the calculate W. This weight is weighted on edges, right? This weight is with edge weight. This one is edge weight. The reason it is in the PPI network, and they give you the edge weight corresponding to confidence. How confident this interaction between two proteins could be. Okay, just be well, this is the edge weight. So they want to calculate the weight on the vortex. They wanted to weight each vortex to see how important. This corresponding to calculate W for every vortex in G1 and G2. And this weight corresponding to importance of vortex U. And how do you judge the vortex? U is important, right? So then in this algorithm, I give you just one example. So let's see just one example, right? The graph. So let's say this is the interaction network, and they do have the weight, right? So this is 1, this is 1.5, and this is 2, and this is 1.0, right? This is no. Okay, that's okay. So I just give you the random number. So let's just say this is A, protein B, C, and D is coronavirus. For some reason, they attack the human, and this is the, let's say this is E, right? And then in this, the data we give to you, we say this maybe it is the virus protein, and this maybe happen to be the human's protein, right? Human's protein. And here you don't need to care about what is the human's protein, what is the coronavirus protein. You just treat them as the one load. And currently we say for each load, you only have the weight for the edges. Now can we to say how important for each load could be, right? So we say just to use a degree may not be enough. And the reason it is maybe this guy, the weight this guy, let's say this is a 1, 1, 1, right? The weight this guy very important. And since the weight is very important, maybe this one has a less degree, but still very important nodes. And also, if what they connect the nodes also very important, this become more important. So this is the global calculation. In this global calculation, the also what they do it is, first they define so the author, what did the author define? The author define to say if, let's go to the paper, right? And the shrinker, let me make sure shrinker is shrinker? Yeah, so please, I kindly unmute you, and all the another student, if you want, I can also unmute you. I just want to make sure that the no much noise as possible. Let me know, everything is fine in your side, right? So how is clear, right? Good. So now, so this is the first step. In even this first step, people consider, if, for example, right, this guy, I use this kind of, this guy, which is leaf loads, right? This is leaf loads. Leaf loads is easy loads, right? This is leaf loads. And this guy, which is an intermediate node, and the importance of each intermediate node depending on adjacent nodes. These leaf loads, easy we can calculate how important this guy, right? And such that the author define. The author, I use the different color to represent the formula. They say if degree, this is what we already talk about, right? Use this one to talk about how many adjacent nodes of this guy. If this node is 1, if degree is 1, in that case, we set up this node. Hold on. So if this is leaf nodes, right? And the also think about it is the leaf nodes, of course, the weight of this guy is, could be very simple, right? And if it's leaf nodes, in that case, what you check that is importance, suppose not include this guy. Because this guy can be easily deleted. Because once you delete that, no other nodes will be totally destroyed, right? For example, if this guy gone, if E is gone, so in that case, although the D got influenced, but the D can still function because the function can be supported by C and B. So that's okay. And most importantly, it is you wanted to judge, what is importance. When they calculate the importance, they say if you delete this guy, and what is influence to another guy. And such that, here I want to erase this one first. A little bit different. The calculated importance of this vortex has been reduced to to calculate this importance, this one is equal to what? Equal to importance importance of all adjacent nodes. Okay, and such that people say to take a look, let's take a look at the WD. And WD is equal to what? WD is equal to the total weight, the total importance between each this guy, right? And then such that you have to calculate the importance of this guy. And so we say that if if the degree, I think this is good. If degree is equal to 1 for U, right? And then for any, if this is any V belong to the label of U, then we set up the weight V is equal to the W U plus W V plus WUV. And corresponding to, since these loads should be deleted, these loads, if you consider the importance of D, right? And this is supposed equal to the summation of all the importance of this adjacent D, adjacent node D, right? Of the importance, this is the, let's say V belong to this one. So it is supposed to be equal to this one, right? Because the importance of this guy is equal to summation of this all these three. And then the question is, how do you calculate this guy, right? So you said, okay, if we delete this guy, if you delete these leaves, and what is the influence? What is the influence of this guy to the adjacent nodes? So corresponding to, you move the weight of E to your adjacent nodes. So in this case, if U is the leaf loads, and V is adjacent of these leaf loads, right? Corresponding in this case, corresponding to WD, part of WD. I use 1 to represent the part of WD came from E, right? This came from E. And this is equal to the WD itself, original D, plus the WE plus the weight DE, corresponding to number 1, right? The 1.0. So this is for if this guy is leaf. Now you can take a look at this guy, these two guys, B and C, right? So, and we say, when you check the adjacent nodes B and C, so the degree of U not equal to 1, right? So in this case, corresponding to larger than 1. And so what we do it is, you consider if this one, if you delete this guy out, if you want to consider the contribution of this guy to the corresponding, the adjacent nodes D. And so you have to, average all this contribution from D to the D, right? Corresponding to the contribution of B come from the weight of B itself, plus the weight from each this guy, right? The adjacent nodes. If the adjacent with A, they have weight A. And if the adjacent with D, they have weight, specific weight. This is 2, right? So you want to get the average contribution and put it back to D, right? So let me use this one. First, I write down the formula. So this is the formula for check the contribution from the leaf loads. And this is the example. This is the example, right? We use this one as example. We say this is, we need to check for the contribution of W. We use the pram to represent this contribution, right? So this is the part of a contribution. So it corresponding to, this is equal to, I write it down here, for example. This is the contribution from W. If we count, this is the delta, right? Delta. So this is a delta from E, delta E, right? We use 1 to represent. This is from E, right? This is called the delta WE. So corresponding to the contribution from the E, and which caused which help to calculate the contribution of D, right? The D's this is the D load, which is important loads. It connects with the 3 loads. So the importance of the D come from the weight itself plus the contribution from each adjacent nodes. And then first you check the leaf loads, right? In this paper, they check all the leaf loads first. And for the discussion, I use this one as the discussion, emphasize 1 node, D, and check the relationship between the B, C, E. And later, we talk about, for this step, what is the general procedure. And then, so take a look at this one. The formula here, it is if the degree U, for example, I want to check B and C, right? And the degree U is not equal to 1. I want to calculate the difference of this one and this B to the D, right? This is the contribution E to B, the contribution E to D, right? So I use this one, use delta to represent the contribution because this is contribution came from E, except the weight itself, right? Can you see that? This is a contribution from E. And then so this one, it is an E for any vortex which belong to U. And what we do it is, we say we calculate the contribution of this weight, right? And so, for example, we check for B, right? So the contribution of this one is equal to W I see. So take a look at this one. If we delete B, in that case, we create when you delete B, so you have two loads got involved, right? Once this one, there's no function, in that case, you want to check if this one no function, what is the influence for this network? So when you delete this one, you will connect the adjacent nodes. In this case, A and D and connected. So you want to calculate the weight for this guy, for this A and E, right? So let's go back to here. We want to check this one since we consider adjacent nodes. And such that we see the new edge, what is the contribution from this new edge? And this is equal to this is we use 1 to represent because maybe you already have another edges here. So if you do have original edge, you put the original edge here, original edge. If you do not have that, you just ignore as a 0. Plus, and this is a plus corresponding to the W, U, the weight of on U, plus, and plus the summation of all these adjacent nodes here, right? All the weight. Because once you delete these nodes, you also delete adjacent nodes, right? And then so you want to check for any adjacent nodes, what is contribution for, this, what is influence for A and E, right? So you make one specific, when you delete this one, if they have adjacent nodes, you make a new line, make a new edge, and you want to calculate the new edge weight. And so this is equal to WU plus W UV. And this is for all the V belong to N, right? NU. And divided by N U NU times NU minus 1 divided by 2. This is normalized. So this NU corresponding to the odd edges and adjacent to U, right? So you use this calculation. I want to draw a line here. So this calculation get the average weight. So you have weight for this guy. And also you have weight for all the adjacent edges. You sum of all this guy corresponding to the total weight on this U and adjacent vertex corresponding to whole contribution divided by all the this is the adjacent edges, choose 2. So use this way you calculate the average contribution. So this one also equal to what we have the delta W, and this corresponding to B to D, right? And you can use the same way to calculate the delta W, C to D. So this what you have the weight for WD is equal to WD itself, right? I use 0 corresponding to original version, right? And do not consider the earning contribution from the just one, the original WD. So if the PPI network do not give to you, you treat them as a 0. And plus the contribution W from the, in this case, from E to D. And from plus the contribution from B to D. Plus the contribution C to D. Can you see? Good. So now I wanted to question. Cannot see? So this is clear, not clear. So in that case, it is question. So this is the formula. This is the formula for these two together. These two together is the formula for calculate the contribution from adjacent nodes. Just like if that is D, we want to calculate D. This is example. Okay? Can you see that? Okay, so I want to double check with you. You can go to the paper. And once you go to the paper, you see here, right? This is the calculation we talk about. This is the calculation we talk about. Can you see that? Or not this one. So the whole thing here, this is the formula we talk about. But when we give it a discussion, I show you an example. I show what is the meaning for that, right? And then so I'll go back to the what we drew here. Okay. So more interesting it is here. I wanted to erase that. Okay, and then erase this one. And more interesting, also stop rotation. Okay, so more interesting in this paper, which corresponded to in this step, still towards step 1, right? When they calculate the calculation, they think about let's check in the way let's check in the order. And once you check in the order, you don't need to recalculate this W0, WD, 1, right? You don't need to do that one more time. Because in the graph, always, if there is not something is not in the order, and it will be redo calculation, right? For example, when you consider this D, you consider the contribution from B, C, E, right? And then another loads, for example, they have another F loads here, and they may connect with C, and then in that case, the contribution from C, you also need to consider the contribution from F. So it's kind of tangled together. So this paper, that what they do it is, so first I give you the formula, then the code, the shooter code similar as that. So first, this is the iteratively make a new G1 prime, G2 prime. You make this new, right? And then you remove leaves. You remove all the leaves. And then, and also at the same time, change the weight. Change the weight on adjacent load. Of leaves. And this corresponding to, if I draw a picture, let's just say draw a picture, right? So in this picture, let's just say, okay, I use this one to draw a picture. So first, you want to calculate the weight, since you need to calculate weight for each this guy, right? Each is u. And the first step, it is you want to calculate the goal of this one to calculate contribution of importance from leaf loads. This is the goal, right? So corresponding to, let's just say we delete this guy, right? If I delete this guy, I use this counter. We delete leaves, right? Leaves corresponding to no adjacent, no, only connect with someone, but do not go to the next one, right? Only have degree one, right? You delete this one by use the function we talk about here. So use this one, you add the W, you change this weight. You change this weight, right? This is the U1, this is U2, right? You change this one, change this weight, because this is adjacent to the leaves, right? You change this one. Can you see? And so this is the second step in this shorter code, in this second sub-step in this big step. And then so the third step, once you leave that, then you have to wait for this guy. Once you leave this guy, think about this line is gone, right? All this gone. So this is the remaining loads. Then you repeat to do that. You repeat to remove leaves in new graph. And then so if there's nothing you can remove, then in that case you propagate So if there is nothing you can remove that, then you repeat these leaves, right? And if there's no, and then you remove the loads which has smallest number of adjacent loads. So you remove these loads, have the corresponding to that loads, the degree of U is a minimum. You wanted to pick up this kind of U to delete. And use this way, propagate out. Then you can use this function, use these two functions. If degree is not equal to 1, right? Then this one, you change the U, get the weight, right? So for example, you delete this one, you got this line, right? Then after that, you repeat this procedure to delete the smallest weight, degree, the vertex which has the smallest degree. If it's the same degree, you randomly pick up one. So in this case, you delete and delete until the last vertex left. And use this way, you use the whole thing here. And you repeat this procedure, right? You repeat this procedure until you repeat this step, the whole thing here, until only one node left. So here we use the new graph. The reason is we don't want to influence the previous graph structure. This is just to use this procedure to get W U for every U in V1, V2, right? So this is from two graphs. Okay, V1 corresponding vertex in the graph 1, and V2 corresponding vertex from graph 2. Okay, so it's clear or not clear for this big step? This is the fourth step. Okay, so let me know if you have any question. So then, we go to the second step. Okay, the second step, let's say this, what is the second step? I'm sorry, it's a little bit noisy here. No, let's just say what is the second step. And here I wanted to make it even bigger. I want to put in the same page. Okay, good. I think maybe need a bit more. Okay, and then so the second step, which is used to calculate pairwise the similarity score. Okay, so you calculate this U, and then so the one more function here corresponding to, we want to calculate as U equal to W U plus lambda. Lambda here is used to calculate what is the edge weight, what is the edge weight contribution, and use W U and V. And this is V belong to NU. So when you calculate this part, you calculate U, right? And this U is help us to know what is contribution from each adjacent nodes from the topology perspective. And then after that, it is that'll be good to check one more time, you check you get the weight for each specific loads. This is from, you do this calculation from G1 and G2. So from the original graph. The previous step here calculates the WU is from the G1 prime and G1 2. And this is a copy, it's the same as G1. It's the same as G1, and this is the same as G2. It's just a copy of that. And use this way, you may remove the leaves and get the smallest number of the vortex, which has the smallest degree, and check the contribution of this vortex, which has the smallest number of degree, right? And do this step, repeat do this step, and check all the adjacent nodes, what is contribution from that. And from here, you may find out when you remove these leaves, and they already count the contribution from the leaves. So the importance of these loads rely on adjacent nodes, and also importance of this one rely on what you do the calculation of the previous this guy. Can you see that? And such that it is so in this procedure, if you think about how to change the code, how to make it better, you can rethink about this procedure. And this procedure, which you can calculate, really depending on the order you pick up from these graphs. If you for some reason, for example, this 2 has the same degree as another 3, right? This 2, if we just take a look at this triangle here, and after all this kind of loads has been deleted, and the weight has been depending on this 3. So, and such that the results of this W is a heuristic. The results is not totally reliable if you next time you change the order to use the vortex. And such that also this is one of the reasons the authors use this one. They said let's check for each vortex not only the importance of adjacent vortex from the topology perspective. I also want to take a look the edge weight, the contribution from the edge weight, right? So this is contribution from the edge weight. In the paper, they use lambda is equal to 0.2. They say when the 0.2, in that case, we consider the importance of this vortex and plus the edge weight of this vortex, and put them all of them together, use as the Philo weight score of S. And then we go to the second step. And the second step, which can't calculate, let me write it down here. It's too much, right? And the second step, which is calculate the pairwise. What happened? Calculate the pairwise similarity score. This is corresponding to compared graphs. And here, we should corresponding to only consider load-to-load similarity. Okay, so this is corresponding to compare two graph, right? As what we show you, and in the various interaction network. So here, let's use this one to represent. I use a different color to represent the different vertex, right? And they may have a different data structure, right? For example, so this is a graph G1, and this is graph G2, and let's say this is the vertex. Let's use still use A, B, C, D, right? So this is the, let's use lowercase a, B, C, D, right? Okay. Okay. So when we take a look, calculate pairwise similarity, so we want to see the whole function here. It is we want to find the mapping G1 to G2, right? This is the goal, is what we want to do. We want to find this mapping. And this mapping, And the most important, it is we want to map loads in G1 to loads in G2, right? Corresponding to, it is this the function we want to get is V1 to V2. Why? The reason it is, if you decide this one, let's use different color. If you see this guy is mapped to this guy, right? And this guy is mapped to this guy, and this, hold on. Let's say this guy mapped to this guy, and C mapped to D, and this guy mapped to this guy, right? This is the E. Okay? So in that case, you can imagine this mapping. So this edge is mapped to this edge, and this edge is mapped to this edge, and this edge is mapped to this edge, and this pass, maybe this pass, or maybe this pass, and for some reason mapped to here. So it's most important, it is you check the vertex to vertex mapping, right? This we need to find the best this mapping, find this function, and such that in the formula. Let's take a look at formula, right? So the author said, okay, let's count the function. The author use A to represent the mapping score. This is just mapping. And have a mapping score, right? The score. Use A to represent the mapping score. And the mapping score for each vertex, pairwise corresponding to pick up one node from one graph and then map to the one vertex in another graph, right? So U is in V1, and V, this is U, right? And V belong to V2. And this is equal to, and also write it down here. They use this one to represent. And in Y, I will show you. So this is, I consider two parts in this calculation. It consider two parts. I want to use another sign. I want to make sure this is the same as the paper mentioned. So they use this one. right? And A UV plus 1 minus alpha B UV. I will show you what is that, right? So A UV corresponding to, in this two part, this part corresponding to importance similarity. Here corresponding to topology, importance similarity, right? And this part corresponding to object, especially it is a vortex to vortex similarity, and corresponding to the sequence similarity. Okay, and so it consists of two parts. We talk about that, right? So, compared to the network, how similar this network, we can treat as this apple, this orange. We want to see how this apple and orange is similar. Except that we have to check the network topology side. The network topology, this is called the HubAlign, right? And the HubAlign, they check the contribution, importance, who could be the hub. What is the possibility this vortex could be the hub loads, right? Could be central loads. This is a HubAlign. So this one is equal to, I use different color. This one is equal to minimum because check the similarity. They have different metrics to measure similarity, SU, SV. S corresponding to the calculation here, this formula. Can you see? Right? Count the importance weight plus the edge weight. Okay? And then the importance weight came from this procedure. Repeatedly remove the vortex in the distance and check the contribution from that, and remove relatively remote vortex, right? And check the contribution by use this formula, this calculation, right? And check what is degree, and check what is average contribution for the importance. So this is A, and then B corresponding to UV. This go to the sequence alignment, same as what we discussed in class. Did you remember we talk about, right? We talk about the longest comma subsequence. And this one, people usually, we don't need to implement that. So people usually use BLAST, this is specific well-studied tool, well-implemented tool. This is a beta score. So this is just some term, this tool, they use that. Check one bit by one bit. Also, you don't need to worry too much about that. It's just this is sequence alignment. The goal of this sequence alignment is to check how similar this apple with the other orange. Or this apple with another, this orange protein with another, orange protein, for example. This coronavirus protein with another with another protein which in the snake. Right? This is the protein in the coronavirus in the human. This is the coronavirus in the snake. And you want to check the similarity they are. So this is the sequence alignment to calculate for a protein to protein similarity, to calculate the vortex to vortex similarity, right? And A count for the structure based similarity. And then so what you do this is A corresponding to the importance similarity. You put them together, you make another function. And then this function, although it's same as A because it came from that. And it's alpha. The author used alpha. The author treat alpha equal to 0.7 by default. Corresponding to most of them came from the topology structure, and just three came from sequence alignment. And corresponding to importance, the vertex importance is very important to decide the function of this network, how similar the two networks could be. For example, you can check coronavirus in human, coronavirus in the cat, and you may find out this similarity score, could be very high, and the contribution from the topology structure part. Topology structure very similar, and it is also, very, in the various biology systems, is also the common things. Okay, so now let's take a look at the third step. And the third step, it is to identify, finally, it is identify the pair. So in this step, you get a similarity score, right? For each pair, And finally, you have to decide this guy should be mapped to A or should be mapped to lowercase c. You have to make a decision, right? Because this mapping is one-to-one mapping. It's one-to-one mapping corresponding to one vertex only mapped to another vertex. And this is not a multiple. It's not a one-to-multiple. This is one-to-one mapping. So now, once you have this guy, right? This one you can see the procedure of this one corresponding to for loop, right? The two for loop. Use two for loop to calculate this one, right? Since this formula is very easy, you get this one, and also you get the matrix. And the matrix here corresponding to, for example, we use this one as example. You have a lowercase a, lowercase b, c, d, right? A, B, C, D. And you have A, B, C, D, E. So in this case, based on the second big step, you have a score for this one. Let's just say, let's say this is 2, and this is 1, this is 1, this is 0, this is 1, and for example, right? And this is 3, and 1, 0, you have different number here. So this is corresponding to the A star, CB, right? A star, IJ. I use this one to represent, right? So the second step, you failed this one. Now the third step, you use to find the mapping. Find the best mapping. For example, you A, lowercase a, map to this guy. You want to use this number. And B, map to D, right? For example, you use this, for example, in this one. Of course, in this case, this number is 0, not supposed to, right? We say B map to C, right? B map to C. So we need to use this one, right? Use this one. Now I want to erase what we wrote. Okay, so so we B map to C, right? And so we use this number. Let's just say make this amount number a little bit big, right? And such that you can feel make sense. It just give you idea. So you get this matrix is not enough. You have to make sure who finally map to whom and use which specific number, right? So you have C, this lowercase c map to D, right? So you have C, suppose map to D here, some number here, right? Use different color. So this guy should be mapped here, right? Corresponding to C is mapped to D, right? And D is mapped to E, right? For example, so they have some number here. So this is finally you need to get the mapping results. You need to figure out this F. This F, A, go to the capital A, and what is the score? And you have B, go to the capital C, what is score? And you have C, let me move it a little bit down. You have C, go to the D, what is score? And you have D, go to the E, what is score? And so the step 2, figure out this matrix, and step 3, need to figure out this guy. Figure out what is this guy, right? So usually, let me erase that to make it even clear. So you have F, A should be mapped to something, right? This map to something. So this is go to the A. Sometimes people, why I erase that? The reason it is sometimes people write in this way. But in this will be depending on how the author take a look at the sequence. This F could be they want to get a number or they want to get an object. So some another version. So we have B go to the C and C go to the D and D go to the E, right? Some another version corresponding to A is equal to capital A. It's corresponding A mapped to A with some score. And the B mapped to some C, right? Based on this function mapped to C with some score. And so this one is the D, for example. Depending on, in this paper, they use what we have here. Okay, so this is the D equal to E. Okay, so finally they need to make this decision based on this matrix. So corresponding to identify the pair of nodes with the highest alignment score. So you can imagine so first what they do it is from all this one they pick up the highest score and then so use this one score as the sales. And then after that it is they check all the adjacent nodes and who has the biggest number score. And then so repeat gradually. This part since it's the easy part, and so I think I just wanted to briefly talk about in this way and use the greedy algorithm. And with the use the greedy algorithm, it is the every time you choose the optimal results and move to the next step, you want to make sure in next step you also get the optimal results for that sub step, right? Same thing here. It is you want to find this mapping, right? You want to make sure this mapping gives you the highest mapping score. So you pick up the highest mapping here from the whole matrix, pick up the highest mapping here, and then so you check the labels and who has the highest mapping. And then you pick up from there. And then after that, you check who is the remaining another one has the highest score. So use this way, you every time, once you expand what you have the graph, and you find the total best alignment. So this is the greedy algorithm. And since once we go to this step, we finish the discussion for the whole this algorithm. So this is the formula we talk about, this guy, right? This one is the formula we talk about. Around here, they also give the picture, some graphs. So this one, it is what we talk about. Okay, so I think maybe that's it. So any more question? Okay, so you think it's much clearer now? Then, so if there's no question, I think maybe for your paper, I just want to stop here. Okay, and so for this algorithm, you can change this algorithm from many perspectives. So you can propose definitely your own algorithm from here, from this paper, and now you can just think about that. Okay, and then so I think maybe for your paper that's it. You can take a look at time complexity, easy to understand, and also this is something the evaluation. I think this is easy to discuss. The shared rotation. What do you mean shared rotation? I'm sorry. So I saw one student ask me question. Srika told me it's very clear, and this is the possible to share a rotation. Bantika, Simpecha. Okay, I think I may need to stop.